Imagine compressing an entire mountain range into a single sugar cube. Now imagine shrinking that sugar cube to the size of a pebble without losing a single gram. That is the level of density we're talking about when we speak of neutron stars. But here's the disturbing truth. Neutron stars do things that should be physically impossible, hinting at forms of matter that may predate the universe itself. Why do some of them glitch as if something is cracking deep inside? Why do others generate magnetic fields strong enough to distort atoms from thousands of kilometers away? And more importantly, what exactly is hiding inside their cores? Something so strange that even our best equations collapse under its weight. Before we venture into the deepest and most exotic interiors of these cosmic monsters, hit like and subscribe to Deep Space Explained, because what you're about to learn will challenge everything you thought you knew about the universe. To understand neutron stars, we start with death, the violent death of a massive star. When a giant star runs out of nuclear fuel, its outward pressure collapses. Gravity takes over, pulling everything inward in a catastrophic implosion. In less than a second, the star's core is crushed with such unimaginable force that protons and electrons fuse into neutrons, forming a super-dense ball of matter smaller than Manhattan, yet heavier than the Sun. This object, only about 20 kilometers across, becomes one of the densest things in the universe. But despite its small size, a neutron star has an interior layered like an onion, transitioning from a fragile crust into a bizarre quantum ocean the deeper you go. And each layer brings new mysteries that our physical models struggle to explain. One of them is so strange that scientists still argue whether it's even real. The surface of a neutron star is not like rock. It's a paper-thin layer of iron nuclei packed tighter than any matter on Earth. Temperatures reach 1,000,000 degrees, yet the crust beneath is unbelievably rigid, stronger than steel by a factor of 1,000,000,000. But here's the twist. This crust is constantly under pressure from the star's violent interior. It sometimes cracks in colossal starquakes, releasing energy that dwarfs any earthquake ever recorded on Earth. But what causes these starquakes? The answer lies deeper, far deeper, in a region no telescope can observe. A region where neutrons may no longer behave like particles and may dissolve into something far more ancient than atoms. Some neutron stars rotate with terrifying speed. A typical pulsar spins dozens of times per second, but millisecond pulsars can reach 700 rotations per second, so fast that the star's equator is stretched by centrifugal force right to the edge of breaking. These pulsars emit beams of radiation that sweep across space like lighthouse beacons. Some are so precise that they rival atomic clocks, maintaining timing stability down to billionths of a second. And yet, suddenly, with no warning, some pulsars jump in rotation. This phenomenon, known as a glitch, suggests something inside the star is snapping, shifting, or reorganizing in an instant. But what inside a neutron star could possibly crack under such pressure? This is where the story takes a dark and unexpected turn. Starquakes are not small tremors. They are catastrophic ruptures of the star's crust. Imagine a shell only a kilometer thick, but with 10 billion times the strength of steel, suddenly fracturing. The energy released can accelerate the entire star's rotation. But as dramatic as these starquakes are, they also reveal something frightening. The crust is under continuous tension from a deeper core that appears to be swirling, shifting, and behaving in ways that break classical physics. It suggests that something beneath the crust isn't stable. and may not even be matter in the traditional sense. To understand this, we need to explore the strange extremes that only neutron stars reach, especially magnetars. Magnetars are neutron stars on steroids, cosmic nightmares with magnetic fields strong enough to tear electrons off atoms from unimaginable distances. Their fields are so intense they can twist space-time and trigger violent gamma-ray bursts detectable across galaxies. One magnetar flare released more energy in 0.2 seconds than the Sun emits in 100,000 years. But magnetars also glitch in ways that cannot be explained solely by starquakes. Some scientists believe that magnetars may partially expose a deeper inner layer, one that cannot exist outside the crushing gravity of a neutron star. A layer that may contain matter in its most primitive possible form. What if neutron stars contain the very same matter that existed microseconds after the Big Bang? Let's return to the deepest mystery, the core. At unimaginable pressures, even neutrons, the supposed last stable particle, may dissolve into their fundamental building blocks, quarks. This creates a smooth, frictionless, ultra-dense substance known as quark matter, or even stranger, strange quark matter, something that does not exist anywhere else in the universe. If such a core exists, neutron stars are not just remnants of dead stars. They are time capsules from the birth of the universe, preserving matter from before atoms, protons, or light could form. Some theories even predict the existence of pure quark stars, smaller, denser, and smoother than any neutron star. Objects with no crust and no internal layers, just one continuous sphere of quark fluid. But this raises a final question, the most dramatic of all. What happens when even quark matter cannot resist gravity? When a neutron star reaches a critical mass, or merges with another neutron star, gravity wins. The object collapses instantly into a black hole, crushing all matter, all quarks, all forces, and all known physics into a singularity. During this collapse, space-time is violently distorted. Gravitational waves ripple across the universe, and elements like gold, platinum, and uranium are forged in the crucible of a kilonova, the universe's most powerful furnace. In 2017, scientists witnessed such an event for the first time. It revealed that neutron stars are not exotic cosmic leftovers. They are furnaces of creation, shaping the periodic table and forging the heaviest elements in existence. Without neutron stars, the universe would have no gold, no platinum, no uranium, perhaps not even planets capable of hosting life. Neutron stars are the universe's strangest laboratories, places where nuclear physics, quantum mechanics, relativity, and cosmic violence collide. They are the closest we may ever get to understanding matter from the dawn of time. Now I want to know what you think. Do quark stars exist, or are they just theoretical ghosts haunting physics textbooks? Comment below, hit like, and subscribe to Deep Space Explained, because the next mystery we explore might take us even deeper into the unknown.